Okay, it's 7 p.m., so let's go ahead and get started today. Hi, good evening, everybody. A happy Monday. We're start of a brand new week of virtual lectures. So, I'm in the same place as I always am in my apartment. So, hopefully everyone's doing safe and doing well. So how's everybody doing? How's your weekend? And, how's everyone, dealing with everything right now? Quiet? Yeah, that's good. It should be quiet. No one should be no one should be out making noise right now. Oh yeah, I see. Yeah, no traffic is good, but yeah, for those who are still working, I think it's definitely really hectic. So yeah, definitely, heart goes out to you guys for sure. Okay. So the plan for today is we're not going to go over any new material today. So the plan for today is to review for the midterm that's going to be a week from today. So the midterm is going to be on April 20th, a week from today. So I thought I'd do a review today just so you guys come and have a week to prepare for the exam. Okay. So based on the poll that I checked about 90 minutes ago, and maybe I should have checked again, the top, there are only 3 things that we can talk about, but here was the ordering. So the number 1 thing was vorticity. So we'll definitely review that. Then we'll have boundary layers. So I think we'll have pretty good amount of time for that too. And then if there's time at the end, then we'll go over in lubrication. But first, I know that there was a question on just the just one kind of step of the lubrication problem on the extra example problems. So at the end of last week, if you caught my email, then I wrote up some more example problems that'll help you for the exam, and I uploaded those on Titanium. So if you haven't checked those out, then definitely check them out, because they they'll definitely help you out quite a bit. Okay. And then besides that, then I think I'll of course answer any questions that you have on those on these topics. But besides that, then I have some idea of what I want to talk about. Okay. Before we get started, let's talk just briefly just on the format of the exam, because it's going to be a bit strange because it's a take-home exam, just as everyone knows. So just like we talked about before, you guys are going to have 24 hours. So what's going to happen next Monday is that I'm going to create basically an assignment on Titanium where the PDF for the exam will be included in there, and then you'll download the exam and then you'll do it in your home. So I basically I made a PDF of the exam basically exactly as I would if I was going to give it to you in class, or I will do that. I'm almost done writing the exam right now. So if you want to print out the exam and you want to write on the exam papers, basically as if we were taking a class, and then scan and upload that, then that works great. If you don't have a printer, or if you don't want to print it out, then you can do the exam on a lined piece of paper too. So that's totally fine with me. So if you're going to do that, just please make sure you clearly label like each question that you're doing, and just give me a little bit of header just to keep it organized. Just so you know, I mean, most of you guys are really good with that on the homework, so I'm not too worried, but I thought I'd just kind of say it just in case. So whether you want to print it out or work on it on your own papers, that's either way is fine with me. So on next Monday, I'm not going to open up a normal Zoom meeting because we're not going to have a lecture that day. But I will be standing by on my computer basically for the entire night. So I'll be eating my dinner during that time, because it's usually I wait until after this lecture to eat. So next Monday at 7, I'll be eating my dinner, but I'll be next to my computer. So if you have questions, definitely just email me, and then I'll get back to you. Hopefully within minutes. That's kind of what I hope to do. And of course the next day, because it's a 24-hour exam, so I'll be standing by my computer basically as much as I can to answer your questions as much as possible. So if you have questions, I think email is probably the best way to do it, just to make sure that just to make sure I get to those questions. Okay. Let me think. I think that's it. I mean, of course, since it's a take-home exam, you'll have all your notes, and you'll have the lecture material, lecture notes, lecture videos, all that will be available to you. So these are, in terms of topics, these are the only topics that are going to be on the exam. So Wednesday, we're going to start something new. Wednesday, we're going to start fluid instabilities, but instabilities will not be on the exam. So we've basically already covered everything that will be on the exam. So, you know, you can basically just study just homeworks 4 and homeworks 5 are you know, definitely good ones to study. Okay. Right, so the question is the email window from 7 to 8:15? So no, so the email window will be for the entire 24 hours. So it'll be from 7 p.m. on Monday to 7 p.m. on Tuesday. I'm not gonna answer your emails at 3 o'clock in the morning, but basically whenever I'm awake, I'll be by my computer to answer your questions. Yeah. So is the review going to be up on YouTube? Yes. Yeah. So I'm recording this lecture basically as if it was another lecture, and I'm going to post it on YouTube basically right after the lecture, just like normal. So you'll have that available to you as well. Mm-hmm. All right. Any last questions on the format for the exam and answering questions that I can answer right now? How many, so the question is how many questions? So it's going to be the same amount of questions. So the same format, where problem 1 is going to be conceptual problems. So this is 40%. Okay. And then there will be 3 problem solving questions. So it'll be problems 2, 3, and 4. Okay. So these will basically be the exact same format as the last exam. So it should be roughly the same length too. So I've already, you know, I haven't given it yet, but I did a practice run for a midterm previous for another class. And that took me a bit longer than usual, but I wasn't taking it under the normal stressful conditions. Because usually when I do my own kind of run of my own exam, I try to emulate the testing conditions where I kind of, you know, turn everything off and I just put a timer in front of my face and I just do the exam. But since it's, you know, a 24-hour exam, I was eating ice cream and eating chips while I was taking it. So I imagine it'll be the same for this exam. So for that other exam, it took me about a little bit over 30 minutes. So we'll see what it is for this question too. Okay. So the question is, when will homework 5 solutions be posted? So that'll be posted first thing tomorrow morning. Mm-hmm. Yeah. All right. Any final questions? So the question is programming required? So so no, it's not. So there's one question kind of similar to the last homework where if you want to plot it using MATLAB or Excel, it can help you, but it's certainly not required. So if you want to plot the basically it's, you know, it's going to be a boundary layer separation problem. So if you want to plot your solution for lambda, it can help, but it's certainly not required. So the question is, are we going to use cylindrical coordinates or spherical? So there's no spherical coordinates, but because, you know, one of the big things here is going to be vorticity. Well, and vorticity, you know, we have a basically rotating flow. So because of that, we necessarily need to use cylindrical coordinates. So if you can use basically the cylindrical coordinates that we've done, you know, up to vorticity, up to this point, and what we cover in the review today, you should be in good shape. But no spherical flow. Yeah. Even I think spherical Navier-Stokes is the bane of the devil. Okay. All right. So I'm using a new app for the note taking. So I bought a new stylus because my first stylus was a piece of crap. So this new one was a lot more expensive, but because of that, it has a lot of nice features. So it comes with an app where I can actually rest my palm on the iPad and still write. And another nice thing is I can actually save the notes as a PDF and upload it on Titanium. So that's another thing I'm going to start doing now too. So after I'm done writing the lecture notes, I'll save the PDF and upload those onto Titanium. Yeah. Yeah. Thank you. I'm glad you noticed right away that my handwriting is a lot better. Yeah, but yeah, buying a Surface Book is expensive, and IT is already kind of putting out tons of fires right now, so I don't think they're going to buy me a Surface Book right now. Yeah. Okay, so there's no more there's no more questions. Let's cover Naveed's question, because I think that's a good one to do. So in the practice problems that I posted online, yes, yeah. So the idea is that because this new app is going to let me basically save the PDF of the notes that I write in class, I can save those PDFs and upload it on Titanium, so they'll be available to you after the class. Okay, so there's a question on problem 1 of the review problems, which was a lubrication problem. Okay. So there was a certain part in this problem where we started with the cylindrical Navier-Stokes and we canceled a bunch of terms, but we're still left with a form that we can't solve yet. So I did kind of a very quick thing that says scale this. So I kind of just want to go over what I mean by that. Okay? So I'm not going to write out the full cylindrical Navier-Stokes because that's really long, but let's just get to the point where we have to scale stuff. Okay? So first we have a UR, DUR, DR. Okay. And this is equal to minus 1 over rho dp dr. Still a bit janky, the writing. Okay. Plus nu times 1 over r d dr. This is kind of the really long term. R dur dr. Okay. Minus ur over r squared plus d squared u r over dz squared. Okay. Okay. So right now we have a very long expression here. So we're not at the point where we can actually solve this for the velocity distribution. Okay. So what I said was, let's leverage the fact that we know that this is a lubrication problem. Okay. And for lubrication problems, we know that we always have a huge difference in length scales. Okay. So let's use the fact that we know that the gap, h, is going to be much less than the radius. Okay. Because basically what we have is a cylindrical piston. Okay. So let's use the fact that the width of the film is going to be much less than the radius, and let's use that to simplify this equation. Okay. So if you remember, when it's been a while since we've done this, but one thing that we've done, I think for a 3-week period was we took Navier-Stokes and we plugged in a scale basically for each of the different terms. Okay. So I'm going to do kind of a half version of that, where it's going to take a while to do the entire thing, but let's just plug in a scale for all the lengths. Okay. So for R, let's plug in big R, R star, okay? And then that's one length. And then for Z, let's plug in the gap height. So we have H times Z star, okay? So basically everywhere that we see R in this equation, we're gonna plug in big R, R star. And then everywhere we see Z, we're gonna plug in H, Z star, okay? And that's gonna help us simplify stuff. So everything else, I'm just gonna leave it alone. So all the velocities, I'm just gonna leave it alone. The pressures, I'm gonna leave it alone. And the viscosities, I'm going to leave alone. Okay. So if we do that, we get this. We get 1 over big R times UR DUR dr star, okay, is equal to minus 1 over big R times rho dp dr star, okay, plus nu, I'm going to run out of space, 1 over r squared times 1 over r star dur dr star, okay. So that's kind of the first half up here. Okay. So then let's plug in for the second half. Okay. Erase what's up here. Okay. So we plug in our scalings for those terms that are down there. What we get is UR divided by big R squared, little r star squared, okay, plus d squared UR all over dz squared times 1 over h squared. Okay. Okay. So now the argument that we're going to make, oh yeah, because I erased, I won't be able to save that, but yeah, maybe next time I'll just turn the page. Still getting used to the new app and stuff like that. Okay. So basically, what we're going to do is we're going to leverage this fact right here and get a bunch of terms that are going to be h over r if we can. Okay. So if we manipulate this such that we get a bunch of h over big R, then we can say that those terms are going to go to 0 because there's such a big difference in between them. Okay. Any questions on this before I turn the page? Okay. Okay. So if we do that, let's look at kind of each of those terms kind of individually, the ones, at least all the ones that we're going to eliminate. Okay. So first we have 1 over r, ur, dur, dr star. Okay. So let me rewrite this a little bit. So let's have this be 1 over h times h over r times ur dur over dr. Okay. So basically, I just kind of slipped in an h over there by kind of multiplying by 1. Because see, we have an h times h on top and an h on the bottom, so those would normally cancel. But I put it in this form such that we can have h over r. So we know that this term is going to go to 0. Okay. Next, we have a nu over r squared. So let's have a nu over h squared times h squared over r squared times 1 over r star ddr star r star dur dr star. Okay. And so since in this term we have an h over r, and in fact the fact that it's squared, we know that this term is going to go to 0, so we're going to ignore that one. Okay. And then finally we have a minus 1 over r squared. So we're going to have 1 over h squared times h squared over r squared times ur divided by r star squared. Okay. And since we have an h squared over r squared, we know that this term is also going to go to 0. Okay. So basically, almost every velocity term with an r in the denominator, we're going to cancel out by scaling. Okay. Okay. So we do that for all the velocity terms. So if you'll notice, our pressure term also has an r in the denominator, but we're going to keep that because we know that we need to keep pressure. As one of the kind of the fundamental things about lubrication theory is that there's always that balance between pressure forces and viscous forces. So our equation basically needs to reflect that. Okay. So after eliminating all of those velocity terms, we finally end up with something that we can solve. So we finally end up with 1 over mu, which is our dynamic viscosity, times dp dr is equal to d squared ur dz squared. Okay. And then finally, this is an equation that we can basically integrate in z, get some velocity, and then basically apply our lubrication theory as well. Okay. Right, so the question is the only condition for lubrication theory to be valid is h less than r? So that's the big one. That's kind of different than most. So you have to have a big difference in scales, such that one length is much less than the other one. But a lot of our other usual assumptions apply. So you have to assume, first of all, that the flow is steady, such that you can cancel out the unsteady term. I mean, you can have unsteady lubrication, but for all the things that we did, we just did steady flow. You have to assume incompressible. You know, a lot of the other standard assumptions also apply, mostly to help you simplify the Navier-Stokes, but the big one is the length scale. So the question is, how come we didn't scale the UR? So normally you would. So normally you would apply a scaling to everything. But for this problem, I just did kind of just a half scale, mostly just to eliminate some of the terms, because when we apply kind of our standard assumptions of like steady and stuff like that, we still end up with a lot of velocity terms such that we can't solve for it. So I did just kind of like a half scale, just with the just for the intent of eliminating those velocity terms. Yeah, but normally you would apply a scale there, but it's but for this case it's okay. Yeah. Okay. Any more questions on how I did this part of the problem? Okay. So then let's start our review. So our first stop is going to be vorticity. Okay. So our vorticity chapter was kind of a weird chapter in that there wasn't too many problems, you know, that you can think of, but there are a lot of really important concepts. So kind of this chapter and the same thing with instabilities. They're kind of what I call kind of like setup chapters for turbulence. So turbulence is kind of the last topic that we're going to learn in this class. But before we get to turbulence, we need to kind of understand quite a few other things. So vorticity is kind of the first of those preparatory topics that we need to cover before we get to turbulence. But with that said, there's still some interesting things with just vorticity itself. Okay. So let's go over that. So this is vorticity. Okay. So just simply, just starting the review, vorticity is simply just the curl of velocity. Okay. So the symbol for vorticity is usually given by this symbol omega. Okay. And the way you compute it is you take the curl, so you take your Nabla operator and you cross it with v, okay, your velocity. And what this basically quantifies is it quantifies the amount of spinning or rotation within the flow. Because for a lot of really complex flows, and you'll see in turbulence too, that one of the most important flow structures are spinning flows. Okay? So this is kind of just a preview, just so you can kind of know where we're going with this. Because as we know, when we have turbulent flow, we have flow patterns that are really chaotic. Okay, so you can have lots of different stuff. Okay, but what tends to happen in turbulent flow is you have kind of these small pockets of flow that rotate. Okay? And basically what we say is that these pockets of flow that rotate, we call these kind of local eddies. Okay. Or more generally, what you'll hear me say is I'll call them just flow structures. But these flow structures are basically just little pockets of vorticity that kind of rotate around. So basically to kind of understand that, or to basically kind of motivate that, that's kind of the reason why I chose to do vorticity. Okay. So in terms of problems, a lot of the problems that you can do with vorticity kind of revolve around our two basic vortex flows. Okay. Okay. So our two basic vortex flows were, one, we had solid body rotation. Okay. Where in solid body rotation, we know that the velocity increases linearly with the radial distance. Okay, so we have u theta is equal to omega times r divided by 2. Okay. Right, and then our other vortex flow, or basic vortex, was our idealized vortex. So the difference between this, between solid body and ideal, is that as you get away from the center, then the velocity is going to decrease. Okay? And in fact, it's going to have a hyperbolic pattern. Okay? So we say that u theta is equal to gamma, which is our circulation, divided by 2 pi r. Okay? So here you have r that's in the denominator, so you know that as r increases, or as you get away from kind of the I guess you can call it like epicenter, or the center of the rotation, then the velocity is going to decrease. Okay. So even though these are relatively simple, they kind of explain, you know, a lot of what we observe in terms of vortex flows in practice and in nature. Okay. All right. Any questions on this before I turn the page? Right, so the question is, do eddies occur because of local differences in viscosity? So that's certainly one cause that they can where that can occur. But actually, a lot of eddies form kind of just purely as an inertial process. So what we'll learn in the next chapter is this idea of instabilities. So even without you know, in the absence of viscosity, what can happen is that if you have flow that's kind of flowing along, then what can happen is if you have some kind of small perturbation, which kind of naturally always happens if you have flow over a rough surface, then that flow just becomes unstable and you just have the flow kind of turning over kind of itself like that. But I think I'll probably say that when we get to instabilities, because, but to answer your question, yeah, eddies can occur because of differences in viscosity, but it can also form in other, from other regions too. So Lewis, your question is circulation in the numerator? Yes, circulation is in the numerator. So it's a gamma divided by 2 pi r. Okay. So the question is, on a solid body, is the angular velocity 0 at the origin and infinite for an ideal vortex? Yes. Yeah, so for a solid body rotation, if you're basically standing at the center, then you experience no velocity. I mean, you'd be spinning, but you know, you wouldn't be you know, you wouldn't have any linear velocity. And then for the idealized vortex, it would be infinite, right? Because you have 1 over, you basically have 1 over 0, and that's infinite right there, or undefined, I guess. Okay. Okay. So let's move on. So the big thing to know, or one of the big things to know, is that from these velocity distributions, you can get distributions for the pressure. Okay. Okay. So actually, you know, I kind of wanted to go over just the process of getting this, because I felt like, you know, in the original notes, I gave you just the how we would solve for it, but then I just kind of threw up the equation to you. So let's actually solve that. Okay. Just so you kind of know where it comes from. Right. So let's do a solid body rotation first. So for solid body rotation, we know that u theta is equal to omega over 2 times r, where r is the numerator. Okay. And then what I said before is if you apply the Navier-Stokes equations in cylindrical coordinates, you would end up with the following equations. Okay, so you get minus rho times u theta squared over 2 is equal to dp dr, okay, and dp dz is equal to minus rho g. Okay. And so basically, you know, these two equations are from the notes. And basically what I said was you would integrate these two equations to solve for the pressure. And I just give you the pressure equation. So let's actually integrate these. Because the integration for this, it's a little bit tricky because, you know, we have actually two independent variables, okay? So from this, we know that pressure is a function of both R and Z. Okay. So if we integrate one of these equations, then the arbitrary constant that comes out needs to account for that fact. Okay. So let's start with this one, just because we don't have to plug in velocity here. Okay. So we have dp dz is equal to minus rho times g. Okay. So if we integrate this with respect to z, then what we get is p of r and z is equal to minus rho gz. So that's simply just the integral of that first term, because rho and g are both constants. We assume that the density is constant. Okay. And then let me actually write this on a new line so it's easier to see. Okay. And since we know that pressure is a function of R and Z, if we integrate simply with just Z, then what we get out of this is not a constant, but we get a function of R. Okay. And so we need to find that function of R, just so basically just so that we can solve for the pressure. Okay. So let's take this expression right here, the one that I'm going to box, and then let's use the other equation that we have. So let's take this and take the derivative. With respect to R. Okay. So then why do we want to do that? We want to do that just so that we can use this other equation right here. Okay. Because if we differentiate this expression with respect to R, on the left-hand side, we'll get dp dr, which is exactly what we have right here. So we can set those equal to each other. And then we can set that equal to the other side of the equation after we plug in for u theta to basically solve for our pressure distribution. Okay. All right. Any questions on this before I turn the page? Okay. Okay, so let's actually perform that differentiation. So like we said, on the left-hand side, we get dp dr. Okay. So we take the derivative of rho gz with respect to r. So there's no r in rho or g or z. So that term's just going to cancel out. Okay. So then in the end, what we get is df dr. Okay. Remember, f was our generic function of r that came out of the original integration. Okay. And so what this is equal to our other equation, which is minus rho times, let's check back on it, rho u theta squared divided by 2. Actually, I don't know why I did that. I have my notes right here with me, so I didn't have to do that. Okay, but just to show you that the other pages still exist and they'll be on titanium later. Okay. Okay. So now let's plug in for u theta. Okay. So we get df dr is equal to minus rho. We know u theta is omega omega r divided by 2. Okay. So we have omega r divided by 2 squared times 1/2. Okay. So we simplify this, we get rho omega squared r squared divided by 8. Okay. All right. Oh, divided by R, sorry. I knew something was weird. Okay. So that's an R there. Okay. So this is 4, and then this is just R. Yeah, sorry about that. So so it was a yeah, negative sign too. Thank you. Yeah, so the coefficient in front of that was minus rho over R, not minus rho over 2. I feel like I do that quite a bit. Right, I substitute R for 2. Okay. Because now what we can do from here is we can integrate, and we can solve for this. Okay. So if we integrate this, we get F of R is equal to minus rho omega squared R squared over 8, okay, plus C1, okay? Where C1, this is just a constant. So it's not a function of R, it's not a function of Z, okay? Okay, so let's plug this F of R back into our expression from before, okay? So we have P of R and Z is equal to minus rho G Z, okay? So that was our expression after we integrated dP dz, okay? Minus rho omega squared R squared all over 8, okay? Plus C1, right? And so we need to apply a boundary condition to solve for C1, okay? So let's apply P at R is equal to 0 and Z is equal to 0. And let's say that this is equal to P naught, okay? So that's going to be equal to C1, okay? So if we do that, then we get this expression right here, okay? So we get P of R and Z is equal to minus rho GZ minus rho omega squared R squared divided by 8 plus P naught, okay? So this is the equation. I think missing a sign. But basically, this is the process on which they use to basically solve for that pressure distribution. So I just want to make sure you guys see that, just so that equation doesn't pop out of nowhere. Okay? And so you can apply basically the same idea for the idealized vortex as well. Okay. Any questions on this before I turn the page? Okay. So for the example here, let's go over just the problem that I posted on titanium. Okay. So this is problem 3 on the extra midterm example problems. Okay. So this is kind of a twist on our tornado problem. Okay. So let's say that we have a tornado. Okay. And this time the tornado is moving. So let's say the tornado is moving with a velocity u naught. Okay. In fact, it's moving towards your house, and there's your house right there. Okay. Okay. So if we basically what the problem says is that if the barometer at your house says that the pressure outside is P sub H, okay. Basically, we want to compute basically how long that we have to evacuate our house if the tornado is coming. So let's say that the pressure on the outside of the tornado is given by P sub C. Okay. So how we want to compute basically how long we have until the pressure at our house reaches P sub C. Okay. And so let's assume that the pressure really far away, P infinity, is going to be equal to 0, just to simplify our calculations. Okay. Okay. So we have basically a tornado. So we know that inside the tornado, or this tornado itself, can be modeled as a Rankine vortex. So I think in the example in class, we looked at the behavior inside the tornado. So inside the tornado, we know that from a Rankine vortex is a solid body rotation. And then outside the tornado, or outside the Rankine vortex, we have idealized flow, or idealized vortex. Okay. So let's use our equation for the pressure for an ideal vortex. Okay. And actually, specifically for the tornado, we have this equation here. So you have minus P infinity minus 1/4 times P sub C minus P naught, where P naught right here, this is the pressure at the center. Times dc squared over little r squared. Okay. Okay. And so what we need to do is we need to compute the distance based on the fact that we know the pressure at our house is P sub C. Okay. Yeah. Imagine sitting down and calculate this. Hopefully you would never be in that situation. But in case you are, then you have this example problem. So you can just plug in all the numbers just really quickly. Okay. So what you need to do is based on the fact, so the only information that we have is just we know that the pressure at our house is P sub H, and we don't know exactly where the tornado is, but we know that the pressure in the tornado is going to be P sub C. Okay? But just from this pressure information and from this equation right here, we can use that to compute the distance between the tornado and the house, because that's basically the biggest unknown here is, you know, how far away is the tornado just based on the pressure information that we have. Okay. So since we're assuming that P sub infinity is 0, so we're just going to go ahead and cancel that guy out. Okay. And then let's solve for R. Okay. Or let's plug in. Okay. So let's plug in P sub H for P of R, and then solve for R. Okay. So we have P H is equal to minus 1/4 times PC minus P naught times DC squared R squared. Okay. Oh, in case you forgot, D sub C, this is the diameter of the tornado. Okay. Right. And then basically we can invert this equation to solve for R squared, which I will do on the next page. Okay. Before we do that, are there any questions on just this part of the problem here? Okay. So if you solve for R squared, then what you get is minus 1/4 times P sub C minus P naught, all divided by P sub H, okay, DC squared. Okay. If you feel uncomfortable with that minus sign, you can flip the sign. So you have 1/4 P naught minus P sub C all over PH DC squared. Okay. And then you can take the square root to find R. Okay. And so from this, we know that this is the distance in between basically the center of the tornado and your house, okay, based on all the pressures that we know. But in this problem, what we're interested in is the distance from our house to the edge of the tornado. Okay. So the distance between house and edge of tornado basically what we can do is we can take this radius and just subtract half the diameter. Okay. So you have 8R minus D sub C over 2. Okay. So this is simply equal to Since this d sub c is squared, we can bring it out. So we have dc times 1 over 4 p naught minus pc over ph minus dc over 2, right? So now we know the distance, and since we know that the tornado is traveling with a velocity of u naught, basically to get time, we can just divide the two. Okay. Okay. So we get t is equal to this quantity divided by u naught. Okay. So we have dc all over u naught, okay, times square root 1/4 p naught minus pc divided by ph, okay, minus 1/2. Okay. Right. So in the case you're ever in a tornado and you know you have a barometer on your house, you can basically use this equation to basically tell you how much time you have to either get the hell out of there or pray. Yeah. Okay. Any questions on this example? Okay. So that covers the the problem solving for vorticity, but I kind of want to go over just quickly kind of the big other conceptual thing. Okay. So the other conceptual thing that we covered in vorticity was Kelvin's circulation theorem. Okay. So it's a theorem with the with the derivation that we went over in class. But remember what it says was for a flow that doesn't have viscosity and the body forces are conservative and the pressure is barotropic. Okay. Yeah. Okay. So if all those conditions are satisfied, then basically no circulation can be generated or destroyed. Okay. So just kind of simply, if you have kind of a say a container of fluid, and all these conditions are specified. Okay. And if this fluid is basically initially at rest, so a fluid at rest basically has no vorticity because it has no or no circulation because there's no motion. Then if you have no viscosity and your body forces are conservative and you have a barotropic pressure, then no matter what you do to this container, basically you can shake it, you can kind of do whatever you want with it. As long as those quantities are met, then no circulation can be created or destroyed in this situation, which is kind of really trippy to kind of think about. So kind of the upshot of this, where like if you do have viscosity, which is for the majority of cases, then viscosity usually acts as a way to generate circulation. And remember, the reason for this is that if you have viscosity, you know, what happens when you have viscosity is that you have the no slip condition. Okay. So if you have the no slip condition, then you know that you're going to have a gradient of velocity. So if you have a gradient of velocity, you basically have different layers where, you know, you have faster fluid over slower fluid, or kind of the vice versa. Okay. So in those situations, if you have like a parcel of fluid just like this, and you have one side of the parcel going faster than the other one, then that's basically going to induce the parcel to spin. So basically, kind of the upshot of this is that whenever you have viscosity, then you're going to have velocity gradients. And usually those happen over a very short period of space. And whenever you have velocity gradients, then because you have different velocity in different layers, that's kind of necessarily going to cause things to rotate. Okay. So those are the two kind of important results for Kelvin circulation theorem, where if you don't have viscosity, then there's no way for circulation to be generated. But if you do have viscosity, then those differences in velocities will cause things to rotate and thus generate vorticity. Okay. Any questions on Kelvin circulation theorem? Okay. Yes. Yeah, so because we have a higher velocity on the top of the rectangle than below, you basically have, you know, a situation like this, where, you know, the top is going to, you know, go faster than the other one. Is going to cause the whole thing to rotate, just like that. Mm-hmm. Not as perfectly as that, but you know, that's kind of the idea. Mm-hmm. Okay. Okay. So there's no more questions. Let's move on to boundary layers. So boundary layers, we talked about it for almost 2 weeks worth of lectures. Okay. Because it's you know, it's a pretty important topic for fluid mechanics. Okay. Okay. Oh, question. When a bucket of water is stirred, only the part that touches the paddle moves with this condition. Yes, that's true. And then that's because the paddle, you know, the fluid has to stick to the paddle basically, and that's going to generate some flow. But basically, because viscosity exists kind of everywhere else in the fluid, that fluid that's in contact with the paddle will cause other fluid to become in motion, which will cause the fluid next to it to come in motion, and then eventually everything will come in motion. I mean, it might take some time, because if you remember when we did unsteady flow, we know that it takes a bit of time for velocity or momentum to diffuse throughout the fluid, but eventually it'll get to that point. Yeah. Exactly. Yeah. So it goes back to that idea of the phase lag when we talked about unsteady laminar flow. Yeah. Yeah. So that's why for a lot of cases it's difficult to kind of examine the fluid during that initial phase. So that's usually called the transient phase, when the fluid is kind of just starting up. It's pretty complex there, so it's usually a bit difficult. So that's why we could only do it with the plate, a moving plate at the bottom. Okay. Okay. So boundary layers. So boundary layers is basically a necessary, you know, thing that results from the fact that we have viscosity. Because as we said, kind of in the previous thing that, or the previous, you know, slide from this, is that whenever you have viscosity, then fluid has to stick to solid surfaces. Okay. Okay. And so because of that, what's going to happen is that you have to have a layer of transition that goes between the surface and any other kind of flow conditions that exist outside it. Okay. Okay. So kind of the quintessential situation for this was we had a free flow that goes over a solid plate. Okay. So let's say that we have some flow up here. Okay. And it has basically a constant velocity UE. Okay. Okay. And then as this flows over a solid plate, what's going to happen is that the fluid that touches the plate, just like we set up there, has to stick to it. Okay. But eventually, you know, that fluid, as you get farther and farther away from the plate, it has to rejoin the free stream condition. Okay. And so what you have is a thin layer of fluid here where this transition occurs, where you go from zero velocity up to something that, you know, UE, which could be something that's really, really fast. Okay. So you have a layer where your velocity is going to transition fairly smoothly. I mean, it's usually a smooth transition, but it happens over a very small period of space. And this, you know, this region where you have basically high velocity gradients, it's, you know, very important, especially for viscous flow, because this is the portion where viscosity has the highest effect. Okay. Okay. Because remember, you know, whenever you have velocity gradients that are really high, then the viscous stresses are going to be really high in that region too. So you need to have, you know, this examining the boundary layer is something that's really, really important. Okay. So the first thing that we went over that's kind of important to know is this idea of the boundary layer thickness. Okay. Because even though I kind of drew it kind of exaggerated here, in practice, this boundary layer is going to be really, really thin. So carefully defining its thickness is going to be, you know, something that's really important. So we went over three definitions. So we went over delta 99, okay, where delta 99 was basically strictly a velocity, you know, definition, where we said that if you travel a distance of delta 99 away from your solid surface, then the velocity is going to be recovered by about 99% of the free stream velocity. Okay, it says delta 99. The next one we went over was the displacement thickness, which we gave it the symbol delta star. Okay, so the displacement thickness, the idea with that is we went over this idea of a mass flow deficit. Okay, because you can see in the boundary layer here that it's not a uniform profile. Okay, so if we kind of make a box here, okay, and we highlight this region right here, then that region you can kind of think of that as the mass flow deficit of the boundary layer. Okay, so delta star, the way that that's defined is that it's the length of zero velocity fluid that has the same mass deficit as the real boundary layer. Where again, you know, that's used a lot in examining kind of aerospace structures, just because it makes the analysis pretty easy. Okay. And then the last one that we went over was theta, which was the momentum thickness, which was kind of the same idea, where because you have this velocity profile right here, you not only have a deficit of mass flow, but you also have a deficit of momentum flow. So the momentum thickness is the thickness of zero velocity fluid that has the same momentum deficit as the real boundary layer. Okay? And just how they're defined, we know that delta 99 is always going to be bigger than delta star, which is always going to be bigger than theta. Okay? So all of them describe the thickness of the boundary layer. It's just they define them in certain different ways, and some are more useful in analysis than others. Okay? So just knowing the definitions are important. And the one actually that we use a lot is the momentum thickness, because later on, once we review the weights method, then we know that we have an explicit formula that lets us compute theta, which kind of unlocks a lot of other things to let us compute, you know, things like delta star, wall shear stress, and separation. Okay. All right. Any questions on this before I turn the page? Right, so theta is the momentum thickness. So momentum thickness is basically one of the ways to define boundary layer thickness. So basically it's the layer of zero velocity fluid that has the same momentum deficit as the boundary layer. Okay? So actually let me kind of explain that just because it's kind of a nice thing to do. So let's say that we have our solid here, and we know that in the solid we have this velocity profile, where eventually it reaches a value of UE, where UE is the free stream velocity. Okay. So if we kind of fill in this empty space right here, this empty space you can kind of think of it as velocity deficit. So that's the velocity that it's kind of missing out on, just the fact that it's in the boundary layer. So what the momentum thickness defines is that if you have a layer of fluid which has no velocity, okay. So that's a 0. So if you have this layer of zero velocity fluid, and these two have the same momentum deficit, not deficity. Okay. And we define the thickness of this layer as theta. Then that's how the momentum thickness is defined. So basically it's the layer of basically zero velocity fluid that has the same momentum deficit as the real boundary layer. Okay. Okay. So then after we did that, we went over the Blasi solution. So we spent quite amount of time on this because what we found was that solving boundary layer equations is extremely difficult. So even in kind of the most simple case of the Blasi solution, we worked on it with with the stream function, and we tried to use a similarity variable, and we got it to the point, eventually where we thought we can solve it, but we couldn't. So we had to rely on numerical simulations. Okay. So kind of the upshot of the Blasi solution is kind of those results from the numerical solution. Okay. So let me just summarize those results here. Okay. Remember, Blasi is the boundary layer solution over a flat plate. So first we have delta 99. Okay. So this is equal to 5.0 times nu x divided by UE. Okay. So by solving the Blasi boundary layer equations, we have an expression for the boundary layer thickness, where the important thing here is we can see that the boundary layer thickness depends on square root of x. Okay. So as we move along the plate, then the boundary layer will grow at the growth rate of square root of x. Okay. So we can get similar expressions for delta star and theta. Okay, so we have delta star over x is equal to 1.72 divided by square root of REX. Okay, and then theta over x is equal to 0.664 divided by square root of REX. Okay, right. So same thing here. These will all grow with square root of x. So if you multiply x on both sides, then you'll see that on the right-hand side you'll have a dependence of square root of x. Okay. It's just that you have a different coefficient in front because we know that delta 99 is the biggest compared to delta star and theta. Okay. Okay. Then we turn the page. And then one other thing that we can find is the wall shear stress, or the skin friction coefficient. Okay. So we know that tau, which is our wall shear stress, this is going to be equal to 0.664 times 1/2 rho UE squared, okay, times square root of nu divided by UE times x. Okay. So from the Blasi solution, you can compute the wall shear stress, given all of these quantities. Right? So this is, this is again really useful. So if you have a flat plate, which seems a little bit niche, but actually, it happens quite a bit. So you can just use these equations to compute these quantities. Okay. So the next thing we covered was transition to turbulence. So basically what we covered was that if the velocity works against an adverse pressure gradient, then the boundary layer will separate. Okay. So usually boundary layer separation is a quantity of really high engineering interest, because if you have boundary layer separation, then what happens is that a wake will form. Okay. And if a wake forms in your fluid mechanics situation, then that changes the behavior really drastically. Okay. So kind of just to give a practical example where, if you're flying an airplane, and if you've heard of the phenomenon known as stall. So stall is really bad. That means you lose all your lift and basically your plane's falling out of the air. So you don't want that to happen. So physically, I mean, it's a pretty complex thing, but physically what happens, or one of the big triggers for stall, is that your boundary layer that goes over your wings and goes over your aircraft will separate, and you get a large wake region. So what happens is that the amount of drag in your airplane will increase dramatically, and your lift will just fall off a cliff. So basically, your plane will fall. Okay. And there's a lot of factors that go into separation, but normally that's really complicated to find out. So the way that that you can actually compute that, at least practically with hand calculations, is to use an integral method. Okay. So this was kind of the second half of our boundary layer lectures, which was integral methods. Okay. So the first thing that we covered was the von Karman momentum integral equations, which I won't go through the derivation of that again. But I want to get, just because we're running a bit out of time, I want to get through to the kind of practical stuff. Okay. Where the method that we apply to a few practice problems now, is Thwaites method. Okay. And so how we got to Thwaites method was we took kind of the results of the von Karman integral equation, and we combined that with some experimental data, and this will allow us to compute a lot of the quantities that's of interest for boundary layers. Okay. So in particular, the first thing that you usually compute with Thwaites method is the momentum thickness. Okay. So we have a formula for that. So we have theta squared is equal to 0.45 times nu, our viscosity, divided by ue to the 6 as a function of x, okay, times integral from 0 to x times ue to the 5th of x dx, okay, theta naught squared times u naught to the 6 divided by ue to the 6th of x. Okay. And so by using the experimental correlations, basically, we have this explicit formula for theta. Okay. So the only requirement here is that you have to know your free stream velocity. Okay. So if you know ue of x, then you can basically plug it straight in there to solve for theta squared. Okay. And then once you solve for theta squared, this will unlock a lot of other things for you. Okay. So the first thing is you can compute the wall shear stress. Okay. So the wall shear stress is mu ue divided by theta times L of lambda. Okay. Where this L of lambda is known as the shear correlation. Okay. And then the other thing is you can compute the displacement thickness. So that's going to be delta star okay, and that's going to be divided by theta. And what this is equal to is some function h, and this h is also a function of lambda. Okay, where this h right here is known as the shape factor. Okay. So both of those functions, L of lambda and H of lambda, those are tabulated. So there's a table that's on the on titanium that will basically compute those for you. Okay. So the key thing that you need to know is you need to know lambda. Okay. So there's a formula for that too, which again depends on the momentum thickness. So for Thwaites method, kind of the first thing that you need to compute is always UE. And then once you have UE, then you compute the momentum thickness, and then from there you can compute a lot of other quantities. Okay. Okay. So before I turn the page, are there any questions on this page? Right. So the question is, do we always assume that theta 0 is equal to 0? So most of the times that you do, unless it's explicitly stated that you don't. So if nothing's stated in the problem, then you can assume that theta 0 is equal to 0. Most of the time, that's a pretty fair assumption, you know, even for a lot of practical problems too. Mm-hmm. Okay, so let me finish this. So I think probably I won't have time to go through the example that was posted, but I can at least walk you through the steps. Okay. Because the last thing that we need to compute is our lambda value. Okay. And this was probably one of the most important. So we have our function from lambda, where this lambda right here is known as the correlation parameter. Okay. So it's going to be theta squared divided by nu times due dx. Okay. Where, you know, if you've computed your momentum thickness already, you have everything that you can plug in here. Okay. And this lambda, in addition to being used to compute the wall shear stress and the displacement thickness, you can use this to determine if the boundary layer will separate. Okay. So if, you know, after you compute this, if there's ever a location where lambda is less than minus 0.09, then your boundary layer will separate at some point. Okay. So remember, you know, because we're working with integral equations, we don't know for sure where, or the location of where, you know, the boundary layer will separate. But if we ever reach a lambda that's less than minus 0.09, then we know that it does separate. Okay. Okay. So we have 1 minute. So let me just kind of breeze through the problem, because a lot of Thwaites methods problems are very similar in structure. Okay. So let me just outline the steps for you, okay, for kind of a general Thwaites methods problem. So if you're doing a boundary layer problem and it asks you to find out if the boundary layer will separate, then you know that the most practical way to do that is to use Thwaites method. Okay. So the first step is to determine UE of x. Okay. So before you do anything, you need to know how your free stream velocity will evolve with x. Okay. So in the case for the problem that I posted, I just gave it to you. But if it's not given to you, then you have to find some way to compute it. Okay. Okay. So once you have your free stream velocity UE, then you can compute the momentum thickness, right? So so the momentum thickness is kind of the thing that unlocks a lot of other things for Thwaites method. So make sure you compute that. So a lot of times that involves, that involves an integral that you have to compute. Okay. And then the last step in order to determine if the boundary layer will separate is once you have theta squared, then you can plug that into the formula for lambda, which will allow you to compute, it'll allow you to determine if the boundary layer will separate or not. Okay. So I know, we kind of ran out of time a little bit at the end right there, but that's basically, boundary layers in a big nutshell. So are there any final questions on boundary layers before I sign off for today? Right, so the question is, why did we try solving for the approximate location of separation in the homework? So a lot of the problems that we've done for Thwaites method is we always do a ratio of x over L. And then, so the reason we do that, if you kind of look back to the lecture problem where we did it for a diffuser, we saw that x over L was only about 0.15. So the kind of approximation, which is a poor approximation, where the boundary layer will separate is only 15% through the diffuser. So that's really small compared to the full length. So we know that the boundary layer will separate, and it will separate at some location from there. So it'll give you kind of a rough idea of like the relative scale. So we know that it's somewhere within the diffuser in that case, but it won't give you kind of an exact location. So for the homework problem, right, so it gives you kind of a kind of approximate window, kind of an approximate scale of where it would do, but not, it can't give you a precise location because it's an integral equation. Yeah. So Lewis, your question is, so will the notes be posted tonight? So I will, once I figure out how to actually do, so I know that you can save it as a PDF, but it might take me a few tries to do it. I also need to eat dinner, so I'll try to post it by tonight, but if I can't figure it out, then by tomorrow morning for sure. Yeah, homework solutions will be up by tomorrow morning as well. Thanks. Yeah, have a good night. Yeah, so sorry, we ran a little bit over today, but this basically concludes the review session. So I'll upload the notes from today. I'll upload the video basically as soon as I can, so you can have that to help you study for the exam. Okay? So have a good night, everybody, and I'll see you guys on Wednesday. Not right now, but I might someday in the future. Are you talking? Is there one that's going to be offered in the fall for next year? On viscid flow. So in viscid flow, a lot of it has to do with like aerospace applications. So that's quite a bit outside my expertise, but I can teach it. I don't know if I would be the best one or the most knowledgeable one for it, but I can probably teach it if the department needs me to. I think right now a lot of things are up in the air just because we don't know what staffing is going to be like next year, and a lot of things are uncertain. So we haven't talked about it as a department yet. CFD. Yeah, that's a good question. I mean, there's a lot of good commercial softwares out there. Actually, there's now that we live in the age of yeah, I see. She's okay. Now that we live in the age of like YouTube videos, there's a lot of great video tutorials that people have posted. So I know that one that is particularly popular, at least among researchers, is called the Open Foam. So let me actually write that out. So I've looked briefly at Open Foam. I've never actually used it, but it seems to be kind of the one that's kind of really flexible and performs really well. The bad thing about Open Foam is that you have to do a little bit of programming with it. But if you can watch some tutorials. So I started to watch one just because I was interested in maybe introducing it either for this class or for 417, which is another class that I'm teaching. But I don't think I'll have time for either of those classes. But I know that one's used quite a bit. I see that name come up. Another one that I've heard is called ComSol. I know that one's a good one. That one has a good reputation for it. If you prefer using something with like a GUI, like something like SolidWorks or something, then ANSYS has a fluid mechanics module with it. I've tried to use the ANSYS fluid mechanics kind of module. It's I had a lot of difficulty with it, but I know a lot of people use it for practical stuff too. The thing with ANSYS is that it's a commercial software. You can download a free version, but the free version is extremely limiting. So you can't really do anything practical with the ANSYS free version. Yeah. Okay. Oh yes, yeah. Star CCM. I've heard of that one too. But I've never actually seen it in action. But I have seen it. I've heard of it. Mm-hmm. Yeah. Usually, if you want to do something, yeah, I hear you. Yeah, the thing is, like with a lot of the software that tends to be taught in classrooms, they use software that's pretty limiting. If you try one of the open source softwares like OpenFOAM, you can tackle problems that are a lot more complex. It's just that the software itself has a much steeper learning curve. But I did see like a 30-minute YouTube tutorial on OpenFOAM, which I started to watch, but I didn't get to the end because halfway through I realized that this would be really hard to cover in just a week. So if we did want to do OpenFOAM in this class, I'd want to do at least 2 weeks on it. That's kind of that's kind of my feeling on how long it would take to at least to get a good feel of it and do at least a pretty decent activity with it as well. Yeah, it's always tough. Currently, no, but I might start something up over the summer. So if you're interested, ping me again at the end of the semester, and then we'll see if we can work something out. I am getting to the stage of my time here at Cal State Fullerton where I need to start thinking about research and start launching projects. So I think the summer would definitely be a good time for that. Yeah. Yeah. So I do a lot of CFD work. So I would spend a good chunk of my funds to get my students access to supercomputing. So even with a software like OpenFOAM, we can throw like a big problem at it, and we'll throw like maybe hundreds of processors at it to make it run. Yeah. So that's generally my what I like to do. Any more questions? No, seems easy. Airdrop. Well, I'll figure this out. Okay. All right, I'm going to sign off. All right, good night, everybody.